Hello, and welcome to our video on some more abstract properties of the Fourier transform. We'll begin with some statements and proofs of parts of Theorem 2.5.4. First, we'll do part 2 on shifts. Take a function f in L1 of R and a number d in R, and define SD on f at x to be f of x plus d. So SD on f is a shifted version of the function f. You shift the graph of f to the left or to the right, depending on what the shift d is. And I'll sometimes call this function f of dot plus d, using my convention of dots to denote the missing independent variable and d the fixed parameter. Then, if f is in L1, SD on f hat at k is e to the ikd times f hat of k. In other words, if you take a function and you shift it, and then you take the Fourier transform of the shifted function, that is just e to the ikd times the original Fourier transform. So let's prove this. We calculate from the definition that SD on f hat at k is 1 over root 2 pi, integral minus infinity to infinity of SD on f at x times e to the minus ikx. And by definition of SD, that is 1 over root 2 pi, integral minus infinity to infinity, f of x plus d, e to the minus ikx dx. And this looks almost like our original Fourier integral, except for the shift inside f, of course, and that is just begging for a u substitution to make it look nicer. So we'll put u equal to x plus d, du is dx. We solve for x equals u minus d. And then we calculate the integral from minus to infinity of f of x plus d e to the minus ikx dx is now the integral from minus infinity to infinity. The x plus d becomes u, the x becomes a u minus d in the exponential, and the dx becomes a du. And then I'll just do the arithmetic in the exponential, so I get integral minus infinity to infinity f of u times e to the minus iku times e to the ikd du. Now look at that last factor, e to the ikd. There is no u at all in that exponential. I can pull it out of the integral. So this becomes e to the ikd times the integral from minus infinity to infinity, f of u, e to the minus iku du. And of course we recognize this integral as the Fourier integral for f hat of k up to the factor of root 2 pi. So we've proved our very useful shift identity. Another thing you can do with a function that surely you did in your happy calculus and pre-calculus days is to dilate or scale it on the inside. And by that I mean you fix a number a in the reals, and we'll take a to be non-zero because otherwise this would be trivial and useless. And we'll denote by f of a dot the map that sends x to f of a times x. So I've scaled f on the inside by this number a. And then the Fourier transform of f of a dot at k is equal to 1 over the absolute value of a times f hat of k over a. So two things to pay attention to with this a. It's a real number because although my function f may be complex valued, f takes in real numbers and spits out complex numbers. And second, I'm taking a to be non-zero. This is apparent in the formula for this Fourier transform where I'm dividing by a in two places. But also if a were 0, then the map x goes to f of ax would just be the constant map f goes to f of 0. And that constant, unless it's identically 0, is not going to be in L1, so it doesn't make sense to talk about Fourier transforms. You will do this proof as an exercise using mostly u substitution and also being careful with when a is positive or a is negative, because that will change a little bit your limits of integration when you write out the improper integral as a limit. Part 4, the transform of the derivative. Suppose we have a differentiable function f on R, and f and f prime are both in L1. Then the Fourier transform of f prime at k is ik times f hat of k. Part 4 is tremendously useful to us. It looks just like the analogous identity that we saw with Fourier series, or the derivative, the Fourier coefficient of a derivative. And we will use this identity often when applying Fourier transforms to solve differential equations. I cannot overstate how powerful and useful this identity will be to us. We might remember it in words as saying that differentiation on the spatial side is multiplication by ik on the Fourier side. And as we already saw with Fourier series, this identity is going to convert a lot of differential equations into somewhat tamer algebraic equations. But that will come next week. For now, let's prove this identity. I claim that if I have a function f that's in both L1 of r and C1 of r, so f is absolutely integrable and it's continuously differentiable on the reals, and if f prime is in L1 of r, then the limit as x goes to plus or minus infinity of f of x is equal to 0. So this is a lovely little proof that I stuck in a footnote for you if you feel like reading it. It's just an invocation of the fundamental theorem of calculus and some definitions of improper integrals. But it's a very nice and satisfying result. I like it a lot. And we're going to use it below. So let's calculate what is the Fourier transform on f prime at k. It's 1 over root 2 pi integral minus infinity to infinity f prime of x times e to the minus ikx. Now, f prime is in L1 of r, so f prime times this complex exponential is also in L1. So I can write my integral as the symmetric limit. This integral from minus infinity to infinity of f prime times e to the minus ikx is really the limit as r goes to infinity of the integral from minus r to r of f prime of x times e to the minus ikx. We remember that existence of the symmetric integral does not imply L1 integrability, but L1 integrability does imply the existence of the symmetric integral limit. So let's integrate by parts on this last integral on the right here. We'll put u equal to e to the minus ikx. Du then is minus ik e to the minus ikx dx. dv is f prime of x dx. And v is f of x. Don't really think there was any other choice here because I'm only assuming that f is 1 times differentiable, so I can't put u equal to f prime and try to differentiate it twice. That would not lead to anything good or possible. So I integrate by parts. I'll just look at this integral from minus r to r. So the integral from minus r to r of f prime of x e to the minus ikx dx, well, that's the expression e to the minus ikx f of x. Evaluate that at x equals r. Subtract from that the evaluation at x equals minus r. And then plus ik integral minus r to r f of x times e to the minus ikx dx. So in integration by parts, usually I subtract off the second integral, but here I had that minus ik from du, so it becomes a plus ik here. Now we know that the limit as r goes to infinity of f of r is 0, and likewise the limit as r goes to minus infinity of f of r is 0. So if I use the squeeze theorem and look at the limit as r goes to infinity of e to the minus ikr times f of r, that's going to be the same as the limit as r goes to infinity of e to the ikr times f of minus r, and that's going to be 0. So here, that little footnoted result that I like so much about f vanishing at plus or minus infinity when it's in L1 and C1 of r, and when f prime is L1, that's where that limit result is really powerful. Because now I conclude that the limit as r goes to infinity of 1 over root 2 pi integral minus r to r f prime of x e to the minus ikx is just going to be ik times the limit as r goes to infinity of 1 over root 2 pi integral minus r to r f of x e to the minus ikx dx. Now, look at this symmetric limit on the right. I have my integral from minus r to r f of x e to the minus ikx. This is the symmetric integral giving the Fourier transform of f. And I know I'm allowed to express the Fourier transform via this symmetric limit because f is in L1. So this is equal to ik times f hat of k. And there we go. Last, I'm going to mention a few other mapping properties of the Fourier transform from Theorem 2.5.5. These are a little more abstract. These are a little harder to prove. In a couple cases, I'll sketch a proof in the notes for you. In a couple cases, I'll ask you to try a proof in the exercises either this week or next week with some guidance. but these are a little deeper and a little more challenging. So first, we saw in several of our Fourier examples, when we just calculated brute force the transform, that if I have a function f in L1 of r, that means f hat is always defined as a function in its own right, but maybe it's the case that f hat is not in L1 of r. Maybe it's the case that f hat is improperly integrable on r, but not absolutely integrable on r. However, it turns out that f hat is always continuous if f is in L1 of r, even if the original function f is not continuous. This is a lengthy, very optional exercise. And also f hat is bounded. We have this sort of Sobolev inequality that the modulus of f hat of k is less than or equal to the integral from minus infinity to infinity of the modulus of f of x, which is just the L1 norm of f. So at worst, f hat is no bigger than the L1 norm of f. That's pretty nice. The Fourier transform is maybe not L1, but sometimes it's a little tamer than your original function, that you have continuity and this global bound over all k. You might reasonably ask, when is f hat in L1 of r? And we will be asking ourselves that question next week. You need some rather strong conditions on f to guarantee this in general. One way to do it is to assume that f is in L1 of r, which of course you would assume, and that f is in C2 of r. That is, that f, f prime, and f double prime are all continuous. That's pretty strong. And you need something else. The limit as x goes to infinity of f of x is 0, and the limit as x goes to infinity of f prime of x is equal to 0. So I mention this because just to show you how much extra work it takes to get f hat back in L1. If you want f hat to be defined, you just take your function f to be in L1. But to get f hat back in L1, you need a lot more on f. We will also be working a bit with the function space L2 of r. We've talked about LP spaces in general, and remember L2 of r, these are all the functions g from the reals into the complex plane. Sorry, that should be reals into c, not c into reals, with the integral from minus infinity to infinity of modulus g of x squared finite. So modulus g squared is improperly integrable over the reals if g is in L2 of r. We should ask ourselves, when is f hat in L2 of r? Trust me, this will be an important thing for us to discuss next week. And the answer is if f is in both L1 of r and L2 of r. So we have two function spaces at play on this slide, L1 of r and L2 of r. We always want our original function f to be in L1 of r for the transform to be defined. For the transform to belong to L1 of r, we need a lot more on f. For the transform to belong to L2 of r, we just need f in L1 and L2. I'm going to conclude with a lot of quotey quotes here. These regularity and decay requirements on f, these requirements of continuity and differentiability and vanishing at infinity, are stringent. They require us to assume much more about our original function than we thought we maybe needed to. But I promise you that for us in this class, at least, these requirements will mostly occur naturally in applications. I had a lot of fun writing that sentence. What do I mean by this? When we are solving actual differential equations with the Fourier transform, the differential equations that we will encounter and want to solve, ordinary or partial, that maybe we couldn't solve easily with prior techniques in the course, or we don't know how to solve some of these PDEs, the various functions that appear in these differential equations will all naturally satisfy the requirements of decay or integrability that we're imposing on this slide. So you do have to be careful when working with the Fourier transform to make sure you're checking off all the hypotheses that the transform lives in the right function spaces. But that won't be too much work for us once we actually get down to the nuts and bolts of the problems, I promise you that.